Hello and welcome. Today, we're diving into something that is, no joke, one of the most important things you can understand to build rock-solid data pipelines. We're talking about the Java Virtual Machine, the JVM, and its memory model. We're going to pop the hood and see exactly what's going on inside so you can build better, more efficient systems. Let's get right into it.
We've all been there, right? It's the question that keeps us data engineers up at night. You've got this pipeline, maybe it's Spark, maybe Flink, and it's humming along just fine for hours, maybe even days. And then boom, out of nowhere, it just dies. What on earth is happening?
And then you dig into the logs and you see this dreaded, infamous error message. It's the smoking gun for sure, but it doesn't really tell you the why. It's just a symptom of a much deeper issue lurking inside the JVM's memory. Well, today we're going to solve this mystery once and for all.
To really get to the bottom of this, we have to go right to the scene of the crime. We need to put on our detective hats and investigate the inner workings of the JVM itself. And the best way to think about the JVM is to picture it as this huge, bustling factory.
So what even is the JVM? Well, at its heart, it's this program that creates a self-contained little world for your code to run in. Your Java or Scala code doesn't just run wild on your computer, it runs inside this virtual machine. And that machine is responsible for managing everything, especially, you guessed it, memory.
And this right here? This is the key. This is the mental model you want to hold on to. The JVM is the factory manager. It's the boss, constantly making calls about where to store all the materials, who gets to use what, and this is crucial when it's time to take out the trash.
Okay, so in our investigation, we follow the evidence. And when it comes to that out-of-memory error, all signs, every single clue, point to one massive location inside our factory. We're talking about the main data warehouse, which in JVM speak is called heap memory.
The heap is the absolute workhorse of JVM memory. I mean, every single object your application creates, every data record you process, every list, every map, it all ends up living here. Anytime you type that little word new in your code, you're basically telling the factory manager, hey, make some space for this new thing in the warehouse.
So, sticking with our analogy, if the JVM is the factory, the heap is its enormous, sprawling warehouse. This is where all the parts, all the products, all of your data gets stored. It is by far the biggest and most important memory space we're going to talk about.
Let's make this super concrete. Say you write this line of code. When you do this, two different things happen in two different places. The actual person object, the thing holding Alice and the number 30, that gets created and stored in the giant warehouse, the heap. But the variable p, that's just a little label, like an address on a piece of paper that tells you where in the warehouse to find the object. And that little label lives somewhere else entirely, a place called the stack.
Now, this warehouse isn't just one giant messy room. No, it's actually really cleverly organized. See, an object's life is like a little journey. It starts its life in a special area called Eden. If it manages to survive a quick cleanup, it moves to a trial area called survivor space. And if it sticks around long enough, proving its importance, it gets promoted to the main long-term storage section, the old generation.
This Scratch notebook analogy is just perfect for those first two areas, Eden and survivor space. Together, they're called the young generation. This whole area is designed for objects that have a really short lifespan. You know, you create it, you use it for a split second, and then you're done with it. Think about processing a single JSON message. The object is a quick note you jot down, and then you immediately tear out the page.
So here's the million-dollar question for us data engineers. What kind of stuff actually gets promoted to that permanent old generation storage? Well, it's all the heavy-duty things we rely on for performance. Your cached RDDs and data frames in Spark, broadcast variables, your managed state in Flink, even the buffers in your Kafka clients, these are the big, important, long-lived objects that are the backbone of our applications.
Okay, so we've got the map of the factory floor, we know about the warehouse and all its different sections. Now we can finally figure out what's actually causing our pipeline to crash. And it all comes down to the factory's cleanup crew, a process known as garbage collection, or GC.
And here it is. This is the heart of the problem, the real villain of our story. When that long-term storage, the old generation, starts to get full, the factory manager basically hits the panic button. It screams, "Stop the world," and brings your entire application to a screeching halt. Why? To perform a really deep, really expensive, full-on cleanup. And we call this a full GC.
This little table makes the difference crystal clear. On one hand, you have a minor GC. That's just cleaning up the Scratch notebook, the young generation. It's super fast, the pause is tiny, and your app barely even notices.
But then you have a full GC. That's when the crew has to clean the entire warehouse. It is slow. It causes these long, painful pauses, and if your streaming job is paused for too long, it's game over.
Now, while the heap is definitely the main character in the story, it doesn't work alone. To get the whole picture, we need to take a quick look at two other key areas in our factory: where the workers keep their to-do lists and where the factory's blueprints are stored.
So this is stacked memory. Every single worker or thread in your application gets its own personal to-do list. When you call a function, an item gets added to the top of the list. When the function is done, the item gets popped right off. It's incredibly fast, super efficient, and totally separate for each worker. Remember that little P variable from before, the address label? That lives right here, on a worker's to-do list.
And this brings us to something that trips up so many developers. A heap error, that out-of-memory error, means your warehouse is full. You have too much data. A stack error, or Stack Overflow error, is totally different. That means a single worker's to-do list got way too long, usually from a function that just keeps calling itself over and over again. Two different problems, two different causes.
And finally, we've got Metaspace. You can think of it like this. If the heap stores all the books in the library, your data, then Metaspace stores the library's card catalog. It holds the blueprints for all your objects, the definition of what a person class is, what methods it has, and so on. It's not the data itself, it's the structure of your code.
And yes, this can absolutely affect us data engineers. You can actually run out of Metaspace. We see this sometimes in Spark when user-defined functions, or UDFs, are written in a way that causes Spark to keep loading tons and tons of new class blueprints. It's a rarer error for sure, but it's a critical one to have in your back pocket.
All right, our investigation is complete. We've identified the suspects, we have a clear diagnosis, now it's time for the prescription. How do we take all this knowledge and use it to become smarter data engineers and build pipelines that just don't crash?
So let's boil it all down. Here is your brand new pocket-sized mental map of the JVM factory. The heap is the warehouse. It's for your data. The stack is the to-do list. It's for execution. Metaspace holds the blueprints. It's for your code structure. And garbage collection, or GC, is the automatic cleanup crew. Simple as that.
So what's the big takeaway here? Well, first, you now have a real understanding of where your data actually lives inside the JVM. You get why your jobs sometimes just pause for no apparent reason. It's that cleanup crew, the garbage collector. You now have the mental tools to start hunting down memory leaks. And most importantly, you see why JVM tuning isn't some dark art. It's a core skill for data engineers. Just knowing how to set the warehouse size with a flag like @XMs can be the difference between a pipeline that fails every hour and one that runs for weeks.
And that's really where we'll leave it. We've handed you the blueprint to the entire factory, so the next time you're building a data pipeline and you decide to cache a big data frame or use a broadcast variable, you'll know exactly what's happening under the hood, you'll know where that data is going to live, so the only question left is, how will you use this knowledge to build your next pipeline differently? Thanks so much for watching.